Hey, what's up, everyone? Welcome to the 2022 USNCO local exam Kinetics section. This is from questions 25 through 30. Let's get started with 25. Dichromate ion is reduced by chloride ion according to the equation below. If the chloride ion concentration is decreasing at a rate of 0.37 moles per liter per minute, how is the concentration of chromium changing? So we're given a chemical reaction here. And the first thing we should do is determine whether or not chromium is increasing or decreasing. Chromium is a product. It's right here. So that means it's going to be increasing. So we can get rid of C and D. And the other bit of information we're told is that chloride ion is the chloride ion is decreasing at a rate of 0.37 moles per liter per minute. And if you look at the stoichiometric rate coefficient for the chloride ion, it's a 6. But the one for the chromium ion is a 2. So that means the chromium is going to be changing at 1/3 the rate of the chloride ion. So 1/3 of 0.37 moles is about 0.12. So our answer is A. Let's go to question 26. The isotope cobalt-57 has a half-life of 272 days. How long will it take a sample of cobalt-57 to decay to 38% of its original activity? Whenever you're asked these types of questions, and these questions have a really similar format, you're going to be dealing with your integrated rate laws. Your integrated rate laws help connect the concentration and the time. So it'll help tell you the concentration at a given time. And in this case, we're told that the isotope cobalt-57, this is indicative of radioactive decay, which is first order kinetics. And so the integrated rate law for first order kinetics is the natural log of the concentration at some time t is equal to minus kT plus the natural log of the initial concentration. We're going to need one more thing in order to solve this problem, and it's going to be the formula for the half-life of a first order reaction. So the half-life of a first order reaction is going to be the natural log of 2 over k. And the natural log of 2 is about 0.693, and so that's over k. And using that, we can find out what the question asks us. So whenever you have a question like this, it's helpful to just assume a certain initial concentration. So let's say our initial concentration, A0, is equal to 1 molar. For this case, I guess I should write cobalt, since we know what element we're dealing with. That's cobalt. The initial concentration of our cobalt is 1 molar, and we're asked how long will it take that sample to decay to 38% of its original activity. So our final concentration, sorry, I keep writing A. Our final concentration would be 0.38, is 0.38 molar. That's 38% of the original concentration. And basically what we're trying to solve for in this problem is T. All right, let's plug in what we have. So the natural log of 0.38 molar equals minus kT plus the natural log of our initial concentration, which is 1 molar. And the natural log of 1 is just 0, so we can cancel that out. We have the natural log of 0.38 molar is equal to minus kT. We're trying to solve for time, so we need to figure out what k is. We can find out k using our half-life formula. So we know that our half-life, T1/2, is equal to 0.693 over k, and we're told that our half-life is 272 days, equals 0.693 over k. And so if you solved for k, that comes out to 2.55 times 10 to the negative third. And there's units, but I just won't deal with the units. And so let's plug that into our old equation that we had. So the natural log of 0.38 molar is equal to minus 2.55 times 10 to the minus third times time. And so if you divide both sides by negative 2.55 times 10 to the negative third, you'll get that your time, your t, is equal to 380 days. And so that's your answer. That's answer choice D. If you have trouble remembering your integrated rate laws and stuff, consider learning the derivation of them. If you know the derivation of them, it kind of becomes intuitive and it becomes less of a memorization thing. I have a video on the derivation if you want to look at it. It does involve some calculus though, so just be wary of that. Let's go to 37. Which statement best describes the variation of the rate constant of a reaction with temperature? The rate constant is dependent on temperature, and the dependence is described by the Arrhenius equation, which goes AE to the minus EA over RT, and that's equal to K. Knowing the formula isn't really necessary for the problem, but this Arrhenius, this is called the Arrhenius equation, and it shows that your rate constant is dependent on temperature. And so let's look through our answer choices to see what best describes that. First of all, we can get rid of A because the rate constant does change with the temperature. B, the rate constant typically decreases. That's wrong. The rate constant typically increases. C, the rate constant typically increases with increasing temperature, because increasing the temperature increases the fraction of collisions that result in reaction. That's true. That aligns with collision theory. There's like 4 increasing on this thing. Whatever. Yeah, basically, as you increase your temperature, the molecules start moving faster and faster. Therefore, you have more collisions, and there's more likelihood that you have more collisions that result in a reaction. D, the rate constant typically increases with increasing temperature because most reactions become more favorable as the temperature increases. What you're doing here is you're relating kinetics with thermodynamics. Thermodynamics tells you whether or not a reaction is favorable or not, whether or not it happens, and kinetics tells you the speed. And you really should avoid connecting them. So D is wrong because you generally don't want to connect thermodynamics and kinetics. Let's go to 28. So the answer for 27 is C. Let's go to 28. A mechanism for the reaction of nitric oxide with hydrogen to form water and nitrogen gas is proposed below. What is the rate law? What rate law is predicted by this mechanism? So let's write out the reaction that we're dealing with. So we're told that we can just actually look at the reaction mechanism that we're given. So N2O2 is an intermediate, so that gets canceled out. That's also an intermediate. So what you're left with is 2NO gas reacting with 2 hydrogen gas to form 2 waters, gas and nitrogen gas. All right, we have to find the rate law that's predicted by this mechanism. The rate law is just going to be the slowest reaction. So the slowest reaction that we have here is going to be this slow irreversible reaction. That's N2O2 gas plus H2 gas reacting to form N2O gas plus H2O gas. And so the rate here, the rate law, is equal to the concentration K times the concentration of N2O2 times H2. I'm just going to put a subscript of 1 here, and you'll see why later on. So the reason this is the rate law is because this is the slowest step. So in a reaction mechanism, you always want to look at the slowest step because that's going to determine the rate of your entire reaction. A factory is only as fast as its slowest worker, if you want to think about it that way. The problem with leaving it as is that N2O2 is an intermediate. N2O2 doesn't appear anywhere in our final reaction. So we need to find some way to get rid of the N2O2 and put it in terms of NO and hydrogen. So how do we do that? You have to look at your equilibrium step. Your equilibrium step tells you, the point of the equilibrium step is that the rate of your forward reaction is going to equal the rate of your reverse reaction. So the rate of your forward reaction equals the rate of your reverse reaction. And the fact that it's fast means that that's not going to be your overall rate law. And And the fact that it's equilibrium tells you that the forward reaction and the reverse reaction happen at the same rate. So we can use that to our advantage. The forward rate has a rate law of K2 times the concentration of NO squared. It's second order because you have that a coefficient of 2 in front of the NO. And so that's going to equal the rate of your reverse reaction. Let's say that's K3 times the concentration of N2O2. So if you wanted to isolate N2O2, N2O2 would equal K2 over K3 times your NO concentration to the second power. We have just isolated N2O2, and we can plug that back into our slow step rate law. So remember, the rate was equal to K1 times N2O2 times your hydrogen concentration, H2 gas, and we just found out that your N2O2 concentration is the same thing as K2 over K3 times your concentration of NO squared times your hydrogen gas concentration. What we can do now is we can take the K1, K2, K3, and we can just all say that's K. The reason we can do this is because K, for all your K's are just constants. So if you multiply a constant by another constant, that's still a constant. If you divide a constant by a constant, that's still a constant. So let's say our constant is, so the rate is equal to some constant K times NO squared times H2. And that is your final rate law. And this one doesn't have any intermediates, it doesn't have any catalysts. So this is a valid rate law for our reaction mechanism, and that corresponds to answer choice B. So B is the answer for question 28. Let's go to question 29. An irreversible reaction A plus B to C is carried out under various conditions, but always with the initial concentration of B being a lot greater than the initial concentration of A. Plots of 1 over the concentration of A as a function of time for each reaction are linear, and the slopes of these plots do not depend on the initial concentration of B. What is the rate law for the reaction under these conditions? Alright, the first piece of information that we're given is the fact that the plot of your of 1 over the concentration of A as a function of time is linear. The fact that it's linear tells you that this is a second order reaction. So the concentration of A, the reciprocal of the concentration of A over time is linear, and it's going to be a positive slope. Remember, if you had just the concentration on its own over time being linear, and it would be a negative slope, this would be first order. If you had the natural log of the concentration over time, if that was linear, that would be second order. But since we have the reciprocal of A over time being linear, this is a second order reaction. So we know our final rate law has to be second order, so we can get rid of A and D. Our second bit of information that we're given is the fact that the slope of these plots do not depend on the initial concentration of B. The slope of your line here is going to be K. It's a positive slope. That's the difference between second order and first. Sorry, that should say first order. That should say zero order. My bad. The difference between your zero order, first order, and your second order is the fact that zero and first order all have slopes that are negative. These have slopes of negative K equals negative K, and your second order has a positive slope of K. The fact that the concentration of B does not affect your slope at all means that your B is not going to be part of your rate law. If the concentration of B doesn't affect how fast the reaction is running, then it's not part of your rate law. So our rate law should not include the concentration of B, so the only answer choice that makes sense is answer choice C. So the answer for 29 is C. Let's go to the last one, which is question 30. The reaction of H2 gas with C2H4 to form C2H6 is catalyzed by metallic platinum. Which statement most accurately describes the impact of changing the catalyst in this reaction? A, the rate of reaction would not change if a greater mass of catalyst were used because the platinum is a solid, so its concentration is a fixed number. That's not true. You can add more platinum and increase the concentration. B, the rate of the reaction would increase if more finely divided platinum were used because the reaction depends on the surface area of the catalyst. That is true. If you have more catalyst and you have more surface area for the catalyst to work on, the reaction runs faster. Think of it as a factory. If you have more workers in a factory, it's going to run faster. It wouldn't run faster if you just had like 100 employees just at the same location. That's why you want more surface area. You want more places for the platinum to be able to react with all your reactants. That's why you would want finely divided platinum. You would grind it up and then that would increase the surface area. So B makes sense. C and D, the delta H and delta S, you don't even have to read the rest of the answer those answer choices because delta H and delta S represent your change in enthalpy and your change in entropy. Those are thermodynamic terms. And remember, you're not really supposed to combine thermodynamics and kinetics. So C and D are wrong. And so B is the right answer. And that was the entire kinetics section of the 2022 USNCO local exam. I hope this was helpful. I hope you were able to learn something, and I hope to see you later. Thank you.